Hello, today's topic is the characteristic equation. This is material from 5.2. So let me just recall where we left off last time. So given a matrix, n by n matrix A, what we have so far is that, so far, we know that given an eigenvalue lambda, we can find or compute, right, an eigenvector v with that value. All right, so remember last time we looked at a certain null space, a certain solution set of a homogeneous determined by this lambda, and we can get actually all eigenvectors with that eigenvalue. That will be the non-zero vectors in the eigenspace. Okay, so that's what we did last time. But, so the question remains is how do we find those lambdas? How do we find those eigenvalues? And so that's the topic of today. It turns out it has to do with solving a certain equation. So let me do this with an example. Let's suppose that A is 2, 3, 3 minus 6. And I want to know the eigenvalues. Well, remember the eigenvectors are non-zero, right? X not 0, such that A minus lambda I x equals 0. Remember, this is the homogeneous system that we solved to find the associated eigenvectors. So what is this? Well, this is saying that we want, to have a non-zero vector where this is a solution means that this is if and only if A minus lambda I is singular. Okay, because one more time, we have a matrix, think of it as a coefficient matrix where you have a non-trivial solution of the homogeneous. That's the same thing, as as saying that the matrix is singular, which of course means not invertible, if you forgot what that meant. Okay. So I'll just say, since non-trivial solution to the homogeneous. Okay. Well, what is the case here? So A minus lambda I, what is it? It's going to be 2 minus lambda, 3, 3 minus 6 minus lambda, right? So I'm thinking of lambda as my unknown right now because I'm trying to find it. But what is A minus lambda? It's just going to be take away lambda the diagonals, right? Remember, whatever you're scaling the identity by, that's going to show up as, on the diagonal as, well, what I'm taking away from A, okay? Well, so I want this to be singular. Now I have an n by n matrix, and well, a few weeks ago now we talked about how we have a nice tool that detects when a matrix is invertible or not, called the determinant. So what we want is that 0 should be the determinant of A minus lambda I, which in this case is the determinant of this guy. It's a 2 by 2 matrix, so I know how to compute it. It's going to be minus 6 minus lambda times 2 minus lambda minus 3 times 3, the product of the off diagonals. Let's simplify this. So I'll FOIL this out. This is lambda squared. Looks like minus 2 lambda plus 6 lambda. So that's a plus 4 lambda minus 12 minus 9, which is lambda squared plus 4 lambda minus 21. And luckily I can factor that as lambda. Let's see, what is that? Lambda plus 7 and lambda minus 3. Okay, so we want 0 to equal that. Well, that means that lambda equals minus 7 and lambda equals plus 3 are my two solutions. And you can check now, those are going to be eigenvalues for this given matrix. Okay, so let's write that down as a definition. That's going to be our recipe for finding eigenvalues. So the determinant of A minus lambda I equals 0, the thing that we were solving before, is called the characteristic equation of A, or for A, or the characteristic equation of A. So what is this? I mean, just notice that det A minus lambda I, right? Lambda is the unknown thing here, right? So this is a polynomial. So what you saw last time here is that when I looked at det of a minus lambda I got a polynomial in lambda, right? Because it involves taking the determinant of this matrix where lambda is on the diagonals. When you do your determinant calculation, you'll get a polynomial, in fact, of degree whatever the size of the matrix. So this guy is a polynomial, and this is called the characteristic polynomial. Polynomial. Okay? And so the fact that we just kind of worked out in the example is that lambda is an eigenvalue for an n by n matrix A if and only if the determinant of A minus lambda I equals 0. So this is kind of the important recipe here. Let me just do maybe one example, e.g. find the characteristic equation for the matrix A. Let me just do a slightly bigger one, but we'll see, not too complicated. 5 minus 2, 6 minus 1, 0, 3 minus 8, 0. I don't know, 0, 0, 5, 4, and 0, 0, 0, 1. Okay, so what do we do here? Well, we want to know, notice that the determinant of A minus lambda I is the determinant of, what do? I take A minus, lambda I means I have a lambda on the diagonal, so this is the determinant of 5 minus lambda, minus 2, 6 minus 1, 0, 3 minus lambda, minus 8, 0, 0, 0, 5 minus lambda, 4, and then the last row is going to be 0, 0, 0, 1 minus lambda. So I want the determinant of this 4 by 4 matrix, which in general is a kind of pain to compute, but here it's upper triangular. So I know that the determinant is just the product of those entries. So the characteristic equation is going to be 0 equals the product of those, 5 minus lambda. Well, notice I have a 5 minus lambda times a 5 minus lambda, then a 3 minus lambda, and a 1 minus lambda. Okay, so this is the characteristic equation. That's what I wanted to find. And note that the, what are the eigenvalues here are, well, lambda equals 5, lambda equals 3, and lambda equals 1. But notice that there's more information now that, right, in my characteristic equation I had powers associated to each one of these roots of the characteristic equation. So we keep track of that. We say that this has algebraic multiplicity 2, right? Because of that factor of 2 up here, all the other guys, these other two have algebraic multiplicity 1 because they only show up with power 1 in the characteristic equation. Okay? So the next thing I want to talk about is what's called similarity. So maybe I'll just give you this definition now and we'll pick up next time. So here's a definition. It's kind of a weird definition, but I want to at least get you thinking about it now. So suppose A and B are both n by n matrices, then we say A is similar to B if there exists another matrix P such that A equals P times B times P inverse. Okay, so note that P should be invertible. Okay, so it's kind of a weird definition. It's probably haven't seen anything like this before, but again, what we're saying here is that A and B are matrices, and I want to say that A and B are almost alike. So the idea is that I can find this other matrix P that somehow I twist B by by multiplying on the left by P and on the right by P inverse, and I get the matrix A. And so remember, be careful that this is not a commutative thing. So I can't just say, well, let's switch the role of B and P inverse to get the the identity there so that A actually equals B. So just note that we're not saying that A equals B, right? This is a looser notion. This is not just saying that A equals B. And the main result here that we'll, well, prove next time, hopefully, is that if A and B are similar matrices, then they have the same characteristic equation. And hence, of course, remember the characteristic equation is what determines the eigenvalues. So if you have two matrices that have the same characteristic equation, they have the same eigenvalues with multiplicity, with those algebraic multiplicity that we talked about. Okay, and so maybe I won't give you the proof here, but it's in the book and we're happy to discuss it. I might somehow fit it into the next lecture, but I think this is a good place to stop. This is, again, this is a notion we'll come back to, as I wanted to at least introduce it here to get you used to thinking about this kind of funny condition of when two matrices are similar. So we'll see you next time.